Okay, so now that you have known about basic rigid joints in Fusion, I will be showing you more complex type of joints and how they can use to simulate more complex systems. So first, I will be showing you Revolute joints. So I have here is a pretty simple 4-bar, and it's made from a series of Revolute joints. And as you can see here, I can just drag the C channel around to simulate movement of a 4-bar in real life. Okay, now I'll be showing you how to actually make this. So these are the C channels I use. Just import them, whatever, you can use whatever length. We're more concerned about the joint here. So first, of course, again, click J to open up the joint menu. And the way it works is the same as a rigid joint. So see here, I have it attached to a point, I have it flipped. And now you have this button here. You can access it either here or on the right side on the joint menu next to motion. So when you click rigid, you'll see a lot of options pop up, and I'll be going over what some of them do later. But first, right now, you want to have a Revolute joint. So what a Revolute joint allows you to do is it allows for the joint, the connection point to spin on the spot, but it doesn't allow it to slide this way in the other axis, but it allows it to free spin. And we want to use a series of this to actually simulate the rotational movement of, in this case, a 4-bar, but you can use it to simulate the rotational movement of quite a lot of different mechanisms in VEX. Okay, after that's done, just press OK. And again, remember, we do need to ground a component in this. See, after that's done, you can basically just rotate this wherever you want. And that's basically what a Revolute joint does. If you had a rigid joint here, this C channel here will be completely fixed to this and you could not move at all. And again, remember to always capture position. Now you've done that, just repeat the same steps. Oh, and one more thing with VEX is that since we had last selected Revolute joint, it automatically pops up. The next joint you make automatically pops up as a Revolute joint. So if you actually don't want this, you can, of course, just change this to whatever joint you want. Okay, now that we have the C channels attached, we can attach the other end of the 4-bar with, again, Revolute joints. And if you'll actually notice here, it actually does not require you to do really anything complex. Once I click the joint button, the series of joints will get actually simulated by themselves, and they will move. Fusion calculates their movement, so it will act exactly like a 4-bar. So you actually don't need to do anything that's rather complicated if you want to make a 4-bar with Revolute joints in Fusion. A lot of things are kind of automated in Fusion, where something like Inventor, you might have to, I don't think you actually do, but you sometimes you might have to add a constraint, let's say for here to here, or something to match their angle the whole time to prevent this bar from tilting. But in Fusion, quite a lot of this is automated. So usually if you can get a series of joints to kind of work in Fusion, it will probably just work, and probably will work in real life as well. Next up, I'll be showing you how to combine Revolute joints with a different type of joint, which is actually called a slider joint, to simulate something like a piston movement, for example, instead of Fusion 360. So this is my finished example. You can see here, if I push this, the piston will extend and in turn turn the C channel. Okay, so let's say you're starting from this step right here, where you have the C channel set up with the Revolute joint, as we talked about. And now the question is how do you actually mount the piston on. So if we go back to before, you can see when we extend this piston, actually the base of it, which is right here, also turns. So therefore what that means actually is we need a Revolute joint. Okay, once you have the Revolute joint attached, you can see the piston can rotate freely on the plane that it's jointed on. And now after that is done, what you want to do is join this and this. And since we don't know the actually distance from here to here, and it doesn't need to be exact in Fusion, what you can do is use the inspect or measure tool. And if you get a number like this, you can always change the precision to a very high number, so you can get the full precision. Okay, now once that's done, you actually have just finished the whole thing. Because you can see, you can just extend this piston, and the entire system will move with it. Now this is obviously a very basic demonstration of where slider joints can be used, and also where slider joints and other types of joints can be used together to simulate a more complex system. Other examples where slider joints could be used are, for example, linear slide, like if you're trying to simulate any sort of sliding motion. For example, if you're trying to build a slingshot or just a linear slide, that's where slider joints are used. But the vast majority of the times they're used to simulate piston movements, because if you really think about it, there's not a lot of mechanisms in VEX that does involve linear sliding motions. Okay, next up I'll be showing you a different type of joint, which is a cylindrical joint. And also I'll be showing you how joints are not always used to simulate motion. It could also be used to make something like a structural design. Okay, so first, this bit here is actually taken from one of my robots I built for Over Under. And what it actually is a triangular bracing piece for a catapult structure. Now, if you are to build this with, let's say, rigid joints, I guess just rigid joints in general, it would be really hard because you'll have to figure out what each of these angles are, the distance is for these. But I'll show you actually easier way to do this. So first, to start off, I already have in this CAD the general structure, and if you really want to follow this, you can just add these together by yourself, or this does really apply to a lot of different things. So first off, what we want to do is add actually a Revolute joint. Now remember what I said when about how Fusion does sometimes make the calculations automatically for you, right? And this is what we are going to be using for this. Okay, now that that's done, what we're going to do now next is use a slider joint between the bearing, and this piece of C-channel. And the reason we're using a slider joint here is because we don't really know the distance this will end up be, because we have a fixed distance from here to here, and this joint is fixed under that spot. So if this is a fixed distance, let's say you type in whatever distance you want, then this joint just simply won't happen. So there's only like one specific distance at which the joint will work, and that's why you need a slider joint. It's because you don't know what the distance will be. Once that's done, we use a different type of joint, which is called a cylindrical joint. What this is basically a slider joint and a Revolute joint combined. The reason we're using this here is because you don't know the distance from this point to here. Obviously, you can't figure that out using the inspect tool, like what I've said before, but often it's just easier to use cylindrical joint. Now you notice once I press OK here, obviously this isn't exactly how it is on the thing I showed you before, but that's because I don't really remember which host stuff is supposed to go on, but you get a rough idea. You see that this triangular bracing here is basically fixed to this pillow block, and the pillow block now has a set distance from here to the C-channel. Now if we try to move this, you'll notice we can't move anything in this, because when Fusion automatically computes all the joints, which is like what this angle is supposed to be, what this angle is supposed to be, the distance here, what's supposed to be, all of them result in basically only one possible solution. Now technically speaking, there's two, because if you drag this all the way to the other side, then it will still work, but that, it usually won't get you in your way when you're designing. If it becomes a problem, then just ground one of the components, and this will be fixed here. And this can be, you can say, abused to make a lot of structural designs like triangular bracing, where often it's really hard to figure out what the spacing is supposed to be. And this could be really advantageous if you use it well, because actually before I learned about this, a lot of my designs were, let's just say, not braced well, and because a lot of it is because of how hard it was to make triangular bracing. And this also goes to show you how joints doesn't exactly need to be demonstrating or simulating motion. It can also be used for structural designs. Cylindrical joints, slider joints, and revolute joints are really the only things you need for Fusion CAD for VEX. You really never make use of the other types of joints because of it's basically impossible to have VEX parts work like those in real life. Now, those joints are great, but they do have one critical error, which is that they are just individual joints working by themselves. So in this case here, for example, we have two revolute joints on two gears, and Fusion just sees these two gears as individual separate components of different systems. But obviously in real life, when this gear spins, the other gear will spin in the opposite direction. Now, that's, for example, here how a double reverse 4-bar will work, because when this arm moves up, this gear spins and move this gear in the opposite direction. But by just using revolute joints, you can see that's not what happens here in Fusion 360. Okay, so how do we actually make it simulate a real life double reverse 4-bar better? So under assemble, you have something called a motion link. What it basically does is it links two joints together, so the motion of one joint affects the other joint, and you can determine what that effect will be. So once you have motion link, all you do is just select the joints that you're trying to link together. Oh, sorry, it appears I already have a motion link. I'll just delete that real quick. Okay, now what you do is you select this joint and this joint, which is the joints you're trying to link together. And once you have this, a new menu will pop up. I'll explain what each of them do here. So this Revolute 9 is the name of the joint, which will probably be this joint. Revolute 8 is this joint, most likely. Obviously, you can change these names under here, joints. Change them to whatever you want them to be. And next to it, we have the axis, which will be, I guess, the thing that you're trying to constrain. In this case, since it's a revolute joint, it can only rotate along the z-axis, so that's the only option that pops up. Under it's an angle value, which I'll explain here, because let's say this gear is 48 tooth, this gear is 48 tooth. So what this means is for every 360 degrees that the Revolute 9, which will be the top joint, rotates, the bottom joint also rotates for 360 degrees. Now sometimes you have to reverse this because the gears will be moving in the same direction, but it just happens in this case you don't need to reverse it, and that's like a little weird thing with Fusion. You don't really know if you need to reverse it or not, so I would just suggest to just do it, see it if it works. If it doesn't, then reverse it. Obviously you can also use animate. It just it's a little weird with Fusion on the double reverse 4-bar, because obviously the C channels cannot collide with each other. Once that's done, you just simply press OK. And now you'll see when I move this up, the two gears actually spin in opposite directions. And now this looks like exactly how double reverse 4-bar is supposed to work in real life. Now motion links are not just limited to gears. It can also simulate a ton of other things, but the vast majority of times you will ever need them is for gears, because other joints like pistons and stuff, it's already like the joints themselves already simulate the movement, whereas gears, because of the way Fusion works or any CAD software works, it does not know that the two can spin in the same direction, and they have to spin in the opposite direction, and this is where a motion link is extremely helpful.